I've shown you this morning that whether you do LES or RANS, you cannot use the full Navier-Stokes equations. That does not work. You need a model. The model is either filtering in space or averaging in time. Whatever you do, you end up with this kind of equations for the average values. And I've told you that you have to average them because of the density problem. If you would do constant density flames, would not be needed. But of course, constant density flames have no application here. So when everything is averaged, we are left with these two terms which we need to discuss. Okay? I forgot to tell you something about this one. But those of you who have already done turbulence modeling for non-reacting flows know that this is called the Reynolds stresses, and this expression is usually modeled with the K epsilon model, with the turbulent viscosity. So I will not discuss this equation because, again, there is no difference as far as turbulence models are concerned in a non-reacting flow or a reacting flow. It's the same equation. Of course, because density is changing, the fields will be different. But you, if you want to model it, you don't care. You just use the same equation. So the two terms which are new and required to be more careful are these two. So we handle this one, saying that we're using a not very good model, but that's the best we can do for the moment. And we are starting to look at that guy, which is the averaged reaction rate. Now, the averaged reaction rate, I told you there are many models which we can use. I started with the models which you should never use, which is basically assuming that the average of a function is a function of the average value. I told you why. And now I want to go and show you what we really do in most codes, actually. So this is the famous eddy breakup model. So the eddy breakup model was written by someone called Brian Spalding. I think he was at Imperial College, I guess. And Brian Spalding looked at this problem and said, okay, let's find a model which would describe what's going on. And again, let's try to derive it, with our hands. So he said, okay, if you look at a flame like this one, and you take a point here in the fresh gases, and the flame never goes there, we know that the reaction rate will be 0. Okay? So if we plot the temperature will look like this, 0, and the reaction rate will be 0. Nothing, the flame is not there yet. If we take a point in the burned gases, and it's fully burned, here the temperature will be 1, everything is burned, and of course the reaction rate will be 0 because there is no fuel left. And he said then in the middle, somewhere in the flame zone where the flame flaps up and down, we'll have a signal where the temperature will go up and down, and every time the temperature goes from 0 to 1 or from 1 to 0, it means the flame front is passing at that point. And so it means we have one shot of heat release. And what we try to do is to measure the average of these things. And you realize this is a very intermittent signal. Most of the time there is no reaction rate, and then suddenly, poof, there is a flame, and then there is no signal, and then there is another flame. So what he said is that what's important at the end, physically, is the number of times in a second where a flame front passes at the place where you are. Physically, that's the most important thing. If you no passage, no reaction rate, here or here, you have a passage, you have some reaction rate. So he started also saying, we'll care about chemistry later. We'll come back to that later. But the important thing is how many times a flame crosses a given location. And this idea of flamelet crossing is the basis of the eddy breakup model. So to measure that, he tried to construct something which is proportional to the number of times where a flame is crossing a given point. Now, obviously, there's one quantity here which is useful to qualify that, and it's the variance of the temperature. Because if you go back to the previous slide, you see that here, there is no variance of temperature, and the reaction rate is 0. On the other side, same thing. And in the middle here, there is a variance of temperature. It's oscillating, and the reaction rate is not 0. So to first order, it makes sense to try to write a model where the mean reaction rate is proportional to the RMS value of the temperature. And now the RMS value of the temperature depends also on another thing. This signal here and this signal here can have the same average value and the same RMS value. The only thing which is needed is that the time where you get 1 here is the same as the time as you get 1 here. It's TB over TB plus TU. So to measure now the number of times where you really have crossing, he introduced a time, which he called tau eddy breakup. This time, and that's for the first time you're going to see the link with the turbulence, this time is the time between two eddies here crossing a given point, you know. So as the number of eddies passing by here, you get crossing on this point, and this time is controlled somehow now by turbulence. So he's going to say that the tau eddy breakup that he has is related to a turbulence time. The turbulence time itself, to have it, you have to go back and see how much information you have on turbulence in this problem. In most cases, if you're using RANS, the only things you have about turbulence is the K epsilon model. And the K epsilon model uses the turbulent kinetic energy and the dissipation of the turbulent kinetic energy. You write equations for K, you write an equation for epsilon. And that's the only thing you know about turbulence. So K is 1/2 U prime square plus V prime square plus W prime square. And epsilon is the derivative of that, the dissipation. So to construct a time with these two things, there's only one solution, which is this one. It says that the eddy breakup time is the ratio of K divided by epsilon. This is a time. And we hope that this time is proportional to the turnover time of the big eddies in this flow. Okay. And it's not too bad. Let's say if you have big eddies in a turbulent flow, they take about K of epsilon seconds to go around. And so when they go around, they create one crossing here, and that's the idea of the eddy breakup model. So here you plug K over epsilon. Here for dimensions, you need to put a density, because this has no dimension. And here you put a constant. As always, when you write a model, if you're smart enough, you put constants that you're going to be able to tune afterwards. Now, the trick, once you've done that, is that still you don't know this. Theta prime square, theta double prime square, is an unknown quantity in your code. You have to express it as a function of something you know. Now, this is where things are convenient, because you can actually prove that if the signal has this telegraphic shape with infinitely thin flame front, then it's exactly equal to theta multiplied by y minus theta. And you can, again, check it easily. If this is the time signal at one point, TB is the time you are burned, TU is the time you are unburned. So we have computed already 5 minutes ago, well, this morning, the average temperature. For the moment, I'm going to worry only about the Reynolds average. And I told you it was TB over TU plus TB. So that's the mean. And if you want the RMS, you need to compute the average value of the distance between the mean and the point. So you need to compute the average of theta minus theta bar square. And you know that this value is equal to TB over TB plus TU. You fill it in here, and you end up with the variance is equal to theta multiplied by 1 minus theta. And then you have closed your problem, because the mean temperature you know. Okay? You know what it is. It's one of the variables of your code. So the eddy breakup model, which you find in 90% today of the code, ends up like this. Theta multiplied by 1 minus theta, the inverse of a time, the density, and a constant. And this model has been incredibly successful. I mean, it's probably the most widely known model for premixed turbulent flames, and it works extremely well. You can convince yourself that it works because you can compare it to experiments. You can take an experiment, a turbulent flame, like this one, and you can go at one point and measure what we call the flame surface density, which is the reaction rate, the mean reaction rate. And this is the kind of curve you obtain. That's obtained from an experiment. And this is what the eddy breakup model gives. The eddy breakup is x multiplied by 1 minus x, so it has a maximum at x equal 1/2, which is here. So the eddy breakup model tells you that the maximum value of reaction rate is obtained just for a temperature which is in the middle. That's the average between the cold and the burn gases. And you see that that's almost what the experiment is saying too. Okay? And you see also how different it is from the model we have for laminar flames, or what I call the no model, I said that you shouldn't use, because this model really does not work that way. This model says combustion takes place only here, very close to the hot gases. But again, it's important to realize that this is real chemistry. This is average quantity. Here, it's an average of temperature, and here it's an average reaction rate. And this is why first, we cannot use this thing. Second, we have to use a model like the eddy breakup, because it captures a lot of the physics of what's going on. Now, the trick is that we know this model is good, but where is chemistry? We started with this equation, and I told you I'm going to average this equation, and then I end up with this thing, which they have nothing in common. Because this thing, I've done it really by hands, you know, and the point is that all the chemistry is gone. Where is the chemistry? Well, the chemistry is in the constant. And as always, when you don't know where things are, they are hidden in the constants. And it's not the first time, you know, I've told you before, for the diffusion, it was already like this. Once more, in these models, everything you don't know how to handle, you put in a constant. The question is, what is the constant? And that's the main drawback of the eddy breakup model. If you compute a given chamber, and you don't know the constant when you start, it's going to be difficult to do it, okay? If you can somehow test a few values of the constants, very fast you will see which one is good, and then you will be able to do variations. You know, more flow rate, more fuel, that will work. But if you want to do a blind test, then the eddy breakup model has this problem that you don't really know what you should put in the constant. And that's a major problem. Another problem, which is also related to this model, is that if you make the flame leaner, so lean that it wouldn't burn, the model doesn't care. There is no chemistry here. So if you keep well, you should put this constant to 0. But as soon as this constant is not 0, it will burn. It doesn't know about chemistry. So it's a good model, but it has limitations, okay? Now, I must give another name here. There's an extension of the eddy breakup model, which is called the eddy dissipation concept. EDC model that you will find in many codes, where they basically try to mix this model with this one. They take the minimum value of the two or something like this. It's a trick which allows to reintroduce a little bit of chemistry. For example, if you say that the reaction rate is the minimum of these two expressions, if this goes to 0, then you will go to 0. But that's not a very well funded approach in general.
Sir, is ED same as EDM?
ED,
EDM dissipation model.
yeah, that's the same. That's the eddy dissipation concept, eddy dissipation model, yeah. EDM. Okay.
We go to the previous slide when we see the slope also is different for the experiment as compared to the AVU model. The slope at both the sides. So can we?
It's a little bit shifted towards, it's not exact, yeah, it's pushed like this. Yeah, 0.6.
So can this also be attributed that we don't have any chemistry?
Sure, of course, yeah. The eddy breakup model is very, very simple. So it's difficult for it to catch everything. But it catches much more than this one. That's the point.
Sir, in the fluent simulation, if you do EDM model, it is ED dissipation model, we don't need any patching high temperature source to ignite the flame. Wherever there is air and fuel mixing, ignition happens. But in EDC concept, ED dissipation concept, no matter how much rich or fuel lean mixer I give, it doesn't ignite.
Well, that's another problem. But it's true that if you talk about ignition in a model like this, it's complicated, okay? if you use this expression, and at one point you set theta to 0.1, then it starts burning. And you cannot stop it because there's no chemistry. If you use a mixture of the two, then of course you need to have something which is sufficiently large here if you want the combustion to begin. Ignition is another story. We'll talk about it in the next days also. Okay, now that I give you approximate model, I want to mention the exact model. There is a model which I will call the ultimate model, which is the PDF model. So who knows what a PDF is here? Okay, not that many people. So we're going to make a small exercise. A PDF, a probability density function, is really not much more than an histogram. Okay, so the histogram today is going to be, we're going to take the PDF of the size of the people not in this room, probably at IIT. Huh? So how would you do that? You would just go outside, ask the first people, are you using international units or are you using feet and meters or feet? Meters, good. Good, not like the Americans. So you would put here the size, and you would get the first guy and say, okay, he's 1 meter 80, so I put a +1 here. Then take the neighbor is 190, then 160. Then if there is another guy at 180, I add it here, and I keep filling this thing. If I fill it sufficiently with all the IIT people, probably 10,000, something like this, and I normalize all that so that the integral is equal to unity, I will find a shape. Okay. And this shape will be the probability of the size, the probability distribution of the size of the people at IIT. Okay. And so that will be then very easy for me to say, okay, what's the probability of finding someone smaller than 150? I just have to go there and integrate from here to there. If I want to find the average size, I just integrate integral of p of theta d theta. And I will get the average size. And so this PDF contains all the information. The trick, and we will use it in a second for combustion, the trick is that the shapes of PDF is a difficult thing to guess. So we can do it here. If we take the shape of everyone at IIT, okay, what do you think the shape will be? I've asked this question 30 times, and I always get the same answer. It's not Gaussian. This is, it's a good example because everyone likes Gaussian distributions, but it's not Gaussian. It's not Gaussian because this is not a male-only institution, as far as I can see. I mean, and so the average size of the women is less than the average size of the men. So we basically are combining two distributions. And actually, I found this picture, which is a good one. That was done in some college in the US a few years ago. So you have the women and the men, and you see that actually, even on a small scale like that, you already have two peaks. And this peak corresponds to the average size of the women. This one corresponds to the average size of the men. And you see on such a simple example that, of course, if you have the PDF, it's finished. You will see that we can solve everything. But the problem is to have the PDF. In other words, the PDF is a complete solution to your problem, but you have no solution for the PDF themselves. And that's a major problem in our community. There are solutions to that, but you will see it's complicated. So let's go back now to combustion. What this means is that if I can at one point know the PDF of temperature, then I can have everything. For example, if I have the PDF, I can have the average temperature. I can have the variance, because if I have P of theta, I can integrate that. And I can have the mean reaction rate, because I know exactly, it's not like before. Before, in the no model here, we only know the average temperature. But now we have much more information. We know not only the average, we know all points here. And so we can integrate the reaction rate multiplied by the probability density function, and then we will have exactly the mean reaction rate. So that's a great method in that aspect. The problem is to find the PDF. And there are quite a few. One of the most famous people there is Steve Pope at Cornell. These PDF methods have been even implemented in Fluent. And it's a method which works, but it's very expensive. And I will tell you why in a second. I don't want to discuss it too much, but I'm sure you will hear about that if you keep working in the field. Just comment on something here. This is, again, something like the Volvo experiment, except that's the French one. And you measure temperature at one point here. And so you get this telegraphic signal. And when you construct the PDF of that, this is where things get complicated. You basically get two peaks. If you take 100 samples, like, we'll have 40 peaks here, everyone is cold, and 50 peaks here, everyone is hot. And in the middle here, you have a little bit of activity here. But the trick is that when you compute this formula, whatever happens here or there does not play a role in the mean reaction rate because there is no reaction rate there. So if you compute omega theta of 0, you find 0, it's the cold gases. And you compute omega theta of 1, you find 0 also. The only thing which is important is these points here. And these points, there are not many of them. It makes sense because these points correspond to the moments where a flame is passing on the point where you measure. And we know that the flame is thin. We know that it's not much time here again where the flame is exactly on your probe. It's passing very fast. And so we have the same problem for PDF model as we would have for the direct resolution if we use the no model, is that there are very few points here. And so you need a big sampling rate to be able to construct this part accurately in order to reconstruct the mean reaction rate. But on the paper, it works. A small issue, I've done the derivation here for a case where before doing the derivation, I have simplified everything. I've told you it's unity Lewis number, single step reaction, constant pressure. And in that case, we only had one variable, theta. But if you want now, and that's the interest of PDF methods, if you want to go to full chemistry, if you have maybe 10 species, then the problem is that you need to move from integral of one variable like this to something which will be integral of omega of y1, y2, yn, t, and then you have what we call a joint probability, which is the probability of having y1, y2, yn, and t at the same place, dy1, dy2, dyn, and dt. The joint probability is what you would expect it to be. It's the probability of having a value of y1, y2, etc. in an interval dy1, dy2, etc. This PDF now is multidimensional. Okay. If I come back to my size question, it would be, for example, in 2D, you could build a PDF of size and weight, for example, for a number of people. And again, the question now, this is only 2D. The question is, how will it look, We already know that the size has two bumps. The weight, we don't know. And the combination of the two gets even more critical. But if you have 20 species, then you must construct a 20-dimensional space. And that's at least very expensive. There are methods to do that. Many of them are based on statistical methods, Monte Carlo methods. But it can be difficult. So let me jump now to flame surface models. So flame surface models are very popular for various reasons. And the idea of these models is to say that we are in the flamelet regime. Okay, that's why they are called flamelet models. So we assume that along this surface here, a little element like this one is like a laminar flame. So this little element that you see here looks very much like the stagnation point flame we were discussing this morning with Shantanu. So the interesting thing when you say that is if this is true, then the mean reaction rate along this surface is nothing else than the surface itself multiplied by the mean consumption speed along this flamelet multiplied by density in the fresh gases. Now, why is it that interesting? Because now you see that chemistry is here. If you have a chemical reaction, for example, if the flame is very lean, you can set that to 0. That allows you, unlike the eddy breakup model, that allows you to take into account chemistry. And turbulence is here. Turbulence is the wrinkling of the surface, and it's taking also into account the wrinkling. So you have the two effects together. You cannot do that outside of this flamelet regime domain that we talked about this morning, that means in the regimes of the diagrams, you don't want to go here, okay? You have to be somewhere in this region. But that's okay. I mean, it covers a very wide region. Now, to use this model, we need two things now. The density of the fresh gases we know, okay? It's 1.17 gram per unit of volume, kilogram per unit of volume, and this is given by you. This thing you need and this we need. To find this thing, there are many different ways to do that, but typically in most combustion code, you know the chemistry, so you have an idea. If this is a flame at occurrence ratio equal 0.8, you know that the unstretched flame speed will be 30 centimeters per second if it's methane. But that's the flame speed of a planar flame front. What happens if now the flame front is wrinkled? What will be the average consumption speed of a wrinkled flame front? This has been the topic also of many DNS in the past. And to make it short, you know, on average, what we see is that there are places which burn less and places which burn more. So here, SC would be less than normal. Here, SC would be more. And when we average that along the surface, when you say that SC is equal to the laminar flame speed, you're good. Compared to the errors that we do at other places, it's sufficient. Okay? You can add corrections, but in most cases, they are not useful. Now, this was for SC. So we have a model for SC, so that at the beginning of your code, you can, you know, have a table saying SC is built this way. If you give me the occurrence ratio, I have a curve for SC like this. So the code can read the occurrence ratio and deduce the flame speed and then use that everywhere in the code here. And if you do a partially premixed flame, that some of you may be interested in, you can compute the equivalence ratio at each point of the simulation and come here and pick up the right value, which means you can, for example, for a flame, I've shown you Prekinsta, you know, yesterday, showing you that there were places where the mixture was lean or places where the mixture was rich. You can come here and read at each point where you are, and so you can take into account local extensions. If a place, for example, is too lean, then automatically SC will be set to 0, combustion will stop. So that's convenient. Now, the main problem is not there actually. We like to work on the consumption speed because, you know, it's easy to write papers when you do that. You do a DNS, you average things along the flame front, and you can say a lot of things, but you don't learn much because the main problem is not to find the speed. The problem is to find the surface. Because the surface is the result of the interaction of the turbulence with the front, and that's much more complicated. So how do you do that? Well, this flame surface density, you have to note that this is a square meter per cubic meters. So if you take a given volume of 1 cubic meters, sigma tells you how many square meters of flame are folded inside this volume. So this is what we plug here. To find it, there are many solutions. If you really want to spend time on it, you can read those papers. You start with the paper of Pope. That's an interesting paper because it was refused, I don't know, 2 or 3 times before someone finally accepted it for one reason. No one understood what was in the paper. It was the first time someone was writing something like this, and it was very difficult to capture. We worked on it later, and there's a paper in JFM here which gives also the derivation of the equation, because the idea is that you can derive an equation for the flame surface density. Now, I have to do it, so I'll do it now. The equation for the flame surface density is not fun. Okay? Sigma itself, when I told you sigma is the surface, you have to realize it's not really like this. It's an average quantity, because sigma is the mean of the surface in the domain where you are at the value of the flame, where you locate the flame. So the definition of sigma itself, that was the paper of Pope actually. If you want to talk about average quantities, you need to worry about what you call sigma. And that's not easy. Once you have sigma, you can derive an equation for sigma, and it doesn't look good either, okay? Now, here, you have variation of sigma, you have a convection of sigma, you have a propagation of sigma because of the displacement speed, and here you have flame stretch, the stretch that we defined 2 days ago. It makes sense because sigma, it makes sense that for the flame surface, the source term should be the stretch because that's what's increasing the value. So if you have a large stretch, sigma will be growing fast. Now, the trick is that, of course, this equation is not closed. You don't know all these things. You know, at the level where you are too far away from your flame, you cannot compute all these values here. You have to close the model. So how do you close it? Well, that's the interesting part. Note also that in this model, there is a small trick here again. You need the displacement speed. And as I've told you, the displacement speed quite often is painful to get. Most people just put here the laminar flame speed, which is may not be such a good idea there. So generally, people don't use this equation. That's the exact equation. They use a simplified equation. That's the one you will find in most codes. So the simplified equation is written like this. Like always, we have put here in a diffusion term everything we could not model with another method. You know, you recognize the famous kinematic turbulent viscosity normalized by a Schmidt number, and again, this Schmidt number will be tuned. And here you have 2 terms, well, 3 actually. Source terms and a sink term. The source terms correspond to stretch. Why do we need a sink term? Well, the sink term is because flame surface sometimes disappear. If you have a flame like this, and you come back a few milliseconds later, probably you will see this. And this surface is less than that one. And the more surface you have, the more chance you have that you will cancel surface. So you need a sink term. So the sink term is located here, and then the problem is to find expression for all that. This is a stretch too, and this is a sink term. How do you model them? Well, the coherent flame model, which is one of the classic model in that field, models them that way. This stretch, we say it's epsilon over k. Here you recognize the same thing we had in the eddy breakup model. It's saying that the characteristic time here of flame stretch is the turbulent time of the k epsilon model. And this one is set to 0, and this one has this funny shape here. It's a sigma square normalized by 1 minus theta. The reason why this thing is written like this is to make sure that when theta goes to unity, so when you're going to the burn gases, you completely kill all the surface. There's an interesting property of this model is that at equilibrium, that means if sigma does not change anymore, these 2 terms are equal, and you recover exactly the eddy breakup model. So this is somehow a generalization of the eddy breakup model, if you will. A more general model than eddy breakup. Now, the problem is, like always in this business, there are many ways to write this model. And again, a few years ago, we went in the literature, and we have summarized here all the various formulations of this model. And there are, I don't know, at least 20. And these equations change depending on what you take for the first, the second, and the third term. And everyone can invent the model he wants. And that's bad, because it proves that no one really knows what we should do. But we talked again not long ago about the FSD model, for example, which is in open foam. It's one of these models, okay? It's another version of all these models. Another way to model the mean reaction rate. Okay, one more jump now in flame surface density models. That's the G equation model. The G equation model is a model where you say, since the flame is thin, let's make it 0 thickness. That's it. Let's say it's an interface. And we are not going to try to resolve what's going on. We just say it's an interface, and we propagate it like an interface. There is an equation, which you will find different names from it. Either the O'Connell equation, I think one of the guys who did it, or the G equation. Sometimes also it's the field equation. And this equation is a method to propagate a front at a given speed. You could say, you know, numerically, you might imagine I take a front, I define it as a surface, and I move it by some Lagrangian method. That doesn't work very well. It's much smarter to write this equation, dg dt plus u grad g equal sd grad g, where sd is the displacement speed, and it's enough then to track g equal g naught here to know where the flame is. And by the way, this equation, you might wonder where it's coming from. Well, you just have to assume that the g field, the field that you're solving for, is such that the isosurface g equal g naught moves with the flame front at speed w. So if it moves with the flame front at speed w, it means that its derivative versus time is 0 if you consider the derivative at speed w. So this leads to that. W is u plus sd grad n. You plug it here, and since these two fields are normal, you obtain this thing. So it's not a big deal, okay? So that's the G equation can be derived like this. So there's quite a few books on that. Norbert Peters from Aachen was one of the guys who pushed that, and Heinz Pitch did it too, where they showed that you can compute turbulent flames with that. The difficulty here is that you need to specify the displacement speed. And the main problem with the G equation is that it's an equation which leads to cusps for obvious reasons. If a flame is like that, and you propagate it at the same speed everywhere, this one propagates too, and you see after some time you are here. And here, you get a singularity, because this point here has to close, and it closes because of diffusion, but we don't have diffusion here. So you cannot use this equation like it is. You need to introduce some correction. Otherwise, when you try to run it, it's just not running. The other difficulty, which is not negligible, is that you end up with a code where you have a density which does this. You have the cold gases. Here you have G equal G naught. And here you have the hot gases. And here, in one cell, you must go from cold to hot. And the density has a big jump. Now, having a code which can survive this kind of gradients is very difficult. So what people do in the G equation, they sicken the flame front. So if you look at the G equation implementation, usually they add a term so that the profile is a little bit smoother, otherwise the code does not work. But that's another possibility. So let me jump now to the second flame model. Now the second, it depends on the scheme, but I would say 4 or 5 usually it's the typical value. Depends on the method you're using.
So the last thing that you put that thicken the boundary is thicken the gradient for that G equation.
Yeah.
Similar to the Thignen model, or?
Well, that's the point. It's you talk to Peters or Pitch, and they tell you we don't do that. We do this, okay? We resolve things on one point. Then you talk to the PhD student, and the PhD student tells you, oh, of course not. We can't. We have to put some second-order term to smooth it, otherwise everything explodes. So in practice, it's not in the papers, but it's in the code. Okay? That's the difference with the second flame model. We start by thickening, and we say it. And then we do the rest. But they don't want to say it. Numerically, it's extremely difficult to resolve a front on 2 points. It's just, especially for density. Okay, second flame model. This one I've already introduced last time. And remember, I told you that there was this property saying that if you multiply an equation like this, diffusion by a factor f, and if you divide chemistry by a factor f, then the speed is the same. That's a rigorous statement. And the flame thickness is more, and it's thickened by a factor f. So this has many interesting properties, that these 2 equations propagate flames at the same speed, but with resolution constraints which are much less. So since our main problem, and I've said that already today, our main problem is that these flames are so thin we cannot resolve them. Let's make them thicker. At least we'll have the right speed, but with a resolution that we control. For example, if the flame thickness is 100 times too small compared to what we can do, let's put f equal 100. And then we'll have at least a flame we can resolve on the mesh. And this is what we did here. I've shown you that already. Once the flame is thickened here by a factor of 20, it's going to be much easier to resolve this front than to resolve that one. Now, of course, when you do that, there must be a price to pay, because otherwise it would be too simple. The price to pay is that the thickened flame does not respond to turbulence like the initial unthickened flame. That's a simple statement, but that's actually a complicated one. We'll need some space here. The first thing you have to realize is that, again, you don't want to be a perfectionist. If you have a big vortex like this, let's say you have a vortex of 1 meter, and here you have a flame which is like 50 microns, and you thicken it 100 times, it won't make any difference for this interaction, because the difference of size between the vortex and the flame is so large that you don't care. It's sufficient. It starts making a difference when the size of the vortex becomes comparable with the size of the thickened flame. So there is an effect of thickening, but not all the time. And this effect can be quantified. And this is what we do. I'm going to show you how we do that. And basically, we have to introduce the winkling. The fact that when the flame is thickened, if the flame is thick like this instead of that, we're going to lose some winkling, and we're going to reintroduce it to a function which we call E, which is here, and which will correct for the effect of the scales that you have lost. So how do you do that? E actually will measure what we call the subgrid scale winkling due to the thickening of the flame. So just an example. This is the DNS of a thin flame. So you can, that's DNS, there's no LES there. So you see we have injected turbulence into this flame. And this leads to a certain amount of reaction rate. Now we're going to do the same thing, but instead of this flame, we are going to thicken it by a factor 5. This is what you obtain. Exactly the same turbulence. You can recognize the structures here. But now, because the flame is larger, it does not react to the eddies in the same way. You recognize, your shape, but, for example, this thing's gone. You didn't see it, okay? But what you can do now is you can measure the difference of reaction rate here and here, which measures actually the difference of winkling between these two things. The initial flame was much more wrinkled than that one. If I would thicken by 50, I would have a flat flame, okay? I can quantify that and put it in what we call an efficiency function. And this efficiency function depends on U prime over SL and L over delta L0, the input parameters of the turbulent combustion model. And then if we know this thing, then our problem is finished, because we can plug it in here, in this function, and now we have an equation which propagates flames at the right speed on a thickness that we control, and which accounts for the subgrid scale winkling which are here.
What is the ratio of R1 by R1 R2, that is F? The ratio of R1 and R2.
Yeah, R1 over R2, R1 over R2, those are the reaction rate. This is the reaction rate here, and this is the reaction rate there. Okay. And it depends on these parameters which are here and on the thickening. So, which really means that when you want to implement this code, we have had a lot of experience with people trying the G equation or the thickened flame model. The thickened flame model is very simple to implement. It's something which works all the time. There's no difficulty with it. So you plug this formula here, and you can apply it to all kinds of problems. Now, again, like all models, a lot of things are hidden here. Okay? But these things are obtained from a DNS at least. That means you do DNS of flame vortex interaction, you thicken the flame, and you measure the result. So you can measure this efficiency instead of doing what we did before, which is to set up a value and hope that it was the right one. So how does this function look? This is a result obtained by, there are two classical models for efficiency. One of them is the Colin model, the other one is Charlotte-Menvaux. And these efficiencies look like this. They are just formula. Okay? You give here the size of the flame. Here you give the size of the mesh. You give U prime, and this thing will give you the efficiency. There are not that many differences between those two, but there are small differences. I just would like you to see that there is a big link between the G equation on one side and the TF-LES model on the other side. Both of them start by saying it's difficult to resolve the flame front. Then the guys of the G equation say, okay, let's make it 0, because propagating an interface might be simpler. And the guys from the TF-LES model said, well, let's make it larger. But in the end, the goal remains the same. In both cases, we want to propagate the flame at the speed SL. There is a big difference still, is that if you look at the equation for the second flame model, you don't see here anywhere a flame speed. Okay? At the input of the code is not going to say SL equal 30 centimeters per second. The input of the code will be to give a chemical scheme to compute this guy, and that's it. And that's a big difference, because in the G equation, you start by specifying the speed of the flame. In both cases, you input some information on chemistry, but not the same. Here, you give a chemical scheme. In the other one, you give a flame speed. And that's the source, actually. We were working with people, because this model is in Fluent, but the people from Fluent don't understand how the model works. So they call it the Poinsot model, and then people call me, asking me why the model doesn't work. It's not my model. I mean, they coded it. It only has my name, but that's, they didn't understand the paper. So, in both cases, also, you have to remember that this is only true in the flamelet regime, so you cannot use it, for all regimes. And when it comes now to Fortran lines to code it, in both cases, you will need a thickness, as I said before. You cannot propagate a front with 2 points. It's extremely difficult.
I have a question. So from G equation, how do you recover the scalars?
You don't. The scalars are not important. You only have G. So in other words, if G is less than G0, C equals 0. If G is more than G0, C equals 1. It's a premix flame, so you don't have any scalars, any additional scalar in addition to C.
I have a doubt in the second flame model, like there's a thickening factor when you give the number of grids that are inside the flame.
Yeah.
So if I vary the grid layer, suppose from 3-4 points to say 10 points, the results show some difference. So when I don't have the experimental data, how to say which one is the right one?
No, wait. Here, when we do the DNS, we do that only to build the efficiency function. Now, when you go into the code now, in an LES code, and you change the mesh, normally the results won't change. That takes into account that. Normally, there's no effect. That's only to do the DNS, that we have different results here and there.
I am like I did LES cases for two cases,
Uh-huh.
same geometry,
Yeah.
and I used different grid points, 3 and say 10. The results were not the same. That's what I'm asking. How do you decide how many grid points you have to use?
Okay, there are many ways to do that. The way we do it now, we have a method where we look at the local grid, and we always impose that we have typically, if this is the flame thickness divided by the local size, we want this to be approximately 5 to 10, which means that we change the thickening as a function of the grid. Okay? We compute the local flame thickness, the local size of the grid, and we change F. I will show maps actually of F pretty soon. Okay, now the second flame model was written maybe 15 years ago for perfectly premixed flames, like all the other models, like the G equation, like the eddy breakup model. But what we found very fast is that we could use it in many other cases. And that's actually the big advantage of the second flame model. So how do you do that? You just have to be careful and to not thicken everything. You know, this operation of thickening here, of multiplying the diffusion coefficient by F is not very nice, okay? Because if you thicken diffusion by a factor of 50, it's a different flow. So you don't want to do it at every point in the flow. You want to do it first only in the flame zone. And remember, the flame zone, in a typical flame, the flame zone is extremely thin. At a given instant, it's only a small fraction of the domain. So the idea was to say, we're going to define a sensor, S, which is 1 in the places where there is a flame, and it's 0 everywhere around it. So far away from the flame, we'll have a normal LES model. In the flame, we'll have the secant flame model. And this is done that way. You just have to use the same model here for the chemistry. And here the diffusion term is written in this way. This is the sensor. So when the sensor is 0, there is no flame, this thing goes to 0, and you're left with the usual diffusion term. So for example, you can compute mixing. If there is a place where you inject pure methane into pure air without combustion, these two things will mix exactly like they would in a normal LES. Then if later combustion starts, S will increase, and in the flame zone itself, S will be equal to unity. This term will go away, and you will be left with the second standard flamelet model. And that's actually a method which allows to compute many flames with this formulation.
Decay is other than decay?
Decay is the diffusion coefficient.
So that is a molecular diffusion?
This one is molecular. That's a good model. This one is molecular. This one is turbulent. And that's the trick. Because when you are in the flamelet model, you should not have turbulent diffusion. Everything is controlled by the secant flame model. Otherwise, you don't control the speed of the flame. So that's a good point. It's a trick. Huh? You have to alternate between the two. So this is what we call the master equation of the secant flame model. And this master equation has multiple applications. For example, in the reaction zones, where the sensor equal to 1, you recover the standard secant flame equation. That's the normal one. If you are far away from flames, you recover the normal mixing model with a turbulent diffusion term. That's also standard. If you're very rich, or if the pressure is low and the thickening of the flame is not necessary, then you can go to F equal 1. The efficiency will be 1, and you're doing DNS. Okay, this is the normal initial DNS equation. The turbulent diffusion goes away, and you're left, this thing goes away, you're left with the normal DNS equations. So this is what we saw at Surfax. I mean, at Surfax, we were doing thickening equal 100 10 years ago. 5 years ago, we were doing 20, and today, many of our simulations are done with 10. So pretty soon, when the computers get better, we'll go to this point. You can also mimic ignition, because you still have chemical kinetics here. In this equation, they are there. So if, for example, you deposit energy, temperature goes up, hop, you will have ignition. In the same way, you can do diffusion flames. This is the most difficult part, actually. We have many examples where it works, but we don't really know why. That's the problem. And there's another nice thing, which is that near walls, the reaction rate goes to 0. Because if the wall is cold, then here, because we have chemistry, exponential minus T over T will go to 0. You must know that that's a big problem. There was a famous story, actually. Henry Weller, Weller? Weller is the guy who wrote OpenFOAM. He's the father of OpenFOAM. He was doing a PhD with us a long time ago. And in those days, there was a problem with the eddy breakup model. Everyone was using an eddy breakup model. And the problem of this model was the following. You would ignite a flame here. It would grow like this. And then it would reach the wall. It would do this. And at the next time step, it would be like this. And everyone was agreeing that it was stupid, okay? Because that was strange. Why was that so? Well, it's easy. It's because in the eddy breakup model and in the EDC model, it's the same. You have theta multiplied by y minus theta and divided by k over epsilon. And when you go near a wall, this thing goes to 0. And since there is no kinetics, the flame accelerates at the walls. Well, it should not. It should stop at the wall. And that's really a good example also of the limits of these very simple models. Since they don't know anything about chemistry, they don't know about quenching at the walls, so they do actually stupid things. They accelerate at the walls. So the secant flame model doesn't do that. that doesn't mean it's doing something right, because it still has the thickening which is active near the walls, but at least at the wall it does not explode. And for a user, you will find out that it's a useful property. So today, well, this slide was written some time ago, for very large chambers, the most extreme case actually is the Siemens cases. You go to high pressure, large chambers, you have thickening factors of the order of 100 to 200. But for small chambers at low pressure, we go to less than 10. Depends on the mesh that you have, of course. As fast as the computer resources increase, we can decrease F. We don't have to change model. At the end, we'll do DNS. So, and the kinetics here, I will give another talk about that tomorrow. Today, we are able to incorporate schemes which have 20 species, so we can do all the chemistry directly into the model. So that's a field.
So, which quantity you are solving, is it a mean quantity, like mean concentrations, or is it an instant response? Because you don't have any average chemical source strength.
Yes, there is a. Well, you can formulate it that way. Since you have filtered your model so that the flame is larger than the grid, you don't have to filter anymore. So indeed, the secant, there's a big controversy in that field. What is the difference between thickening a flame and filtering a flame? You can derive actually secant models from filtering, and this has been done by different teams. But at the end, we keep using the secant flame. But you're right, we don't have to filter this term. It's already secant. It's secant sufficiently to be resolved on the grid, so we don't do anything more.
In the last slide, when you're saying that the F will go down
Next one.
So when you say that F goes down when the computer resources are increasing, what do you mean is that we have finer grids?
Yeah, sure. As soon as the grid is finer, then you can use a smaller value of F. But you don't have to. If you don't have a fine grid and a big computer, you use a larger value of F. You lose something, but at least you can run your simulation. So that's a typical example of the fields now that you can have. So this is the thickening factor. So you see here the place where we thicken, that changes with time. Okay, you come back after 5 milliseconds and we are thickening in another zone. The sensor, the flame sensor, tells you where you should thicken, and then you can see the values up to 45. And the efficiency is really the wrinkling of the flame. So we compute the reaction term and we multiply it by 4, 5, 6, etc. If you would use the no model, you would multiply by 1 only, okay? Because the no model, the one I told you not to use, would have no correction, so it would just set it to 1, which is not a good idea. Okay, I'd like to come back again now on this no model question. It's very strange because 10 years ago everyone knew that it was not a good model, but now we see teams trying to do it and trying to sell codes. They even do it with complex kinetics. An interesting question, and that's really a numerical question, is how come that something which is not physically based can still work? Okay, and that's actually a good question. Normally, we should not be able to use these codes to do a computation because we don't have enough points to resolve the flame front. It shouldn't work. But it works. It works. Even so, we have a mesh which is 1 millimeter, and we know that the flame thickness is less than 50 microns, and still it's working. So why does it work? It's working for a strange reason. It's working because of artificial viscosity in the code. In all of these codes here, typically Converge, for example, in Converge, the equation which is really solved is this one with a turbulent diffusion. And here there's something I will describe tomorrow, which is an artificial viscosity due to the scheme itself, because of time advancement, because of space advancement. Now, this really means that the viscosity which is there in the code is much larger than, wait, I'm going to stop, much larger than the normal viscosity. And this is what makes the code work, because what we should have is this. This is the mesh. The reaction rate is not resolved on this mesh. The true reaction rate is not resolved. But you put that in your code with a lot of artificial viscosity, and after one time step, you have this. And so you smooth out, and again, you thicken the flame front, like everyone else. There's no mystery. You cannot resolve a 50 micron front with a 1 millimeter mesh. That's just impossible. But The diffusion does it for you. The diffusion of the scheme scrambles the whole thing so that it does not explode, but it's not a reasonable result. Okay, I'm going to stop here. We take a short break. If you have questions, it's the right time. We'll finish this session by discussing now the models for diffusion flames. It's important to realize that everything I've told you was in a very limited framework of applicability. It was premixed flames, Lewis equal unity, adiabatic, single step, etc., etc. So I'm going to take another extreme case, which is diffusion flames. Diffusion flames, again, Shantanu mentioned that this morning, and again, really the Z diagram and the mixture fraction is the essential element of most diffusion flame models for turbulent cases. There's a famous place, which is the TNF workshop, where you can find all kinds of examples. Just to remind you how a flame looks like when it's a diffusion flame. So this is a jet here of fuel, and there is quiescent air, and this is LES, and you see the structures here on this flow. It's an LES, and you see how long those flames are, and you see how lazy they are too, and now it's slowed down, and you can see these structures here. And we believe that many of these structures actually are iso Z surfaces where we are at the stoichiometric value. So this is where combustion takes place. You remember what was said yesterday, that these zones can be split in two, a lean zone here, a rich zone inside, and in the middle, the flame. Okay, that's where the flame is sitting. So how do you model that? Well, there's, again, it's not a full list. It's just a few models I want to describe here. I will talk about PDF models. I will talk about flame surface models, exactly like we had for diffusion flames. CMC models, I will just mention them because those things get complicated, but Shantanu can tell you about them. Linearity models I will not describe, and I will talk again about the second flame model fast. So let me start with the basic tool, again, is going to be the Z diagram. When you have derived this Z diagram many times now, yesterday and this morning, we didn't say that the flow was laminar. Okay? We didn't have to. Everything was written looking at the full equations. In other words, this diagram holds for laminar flames, and it holds also for turbulent flames. So we should use it if we have a turbulent flame. How are we going to do that? Well, that's an example of a code which would work for turbulent cases with the Z diagram. You would, in this code, solve this equation. And as I told you yesterday, this equation is much simpler than the full equations. And once you have solved this equation, it would provide the Z field at every instant and every point. If you have the Z field and you know the link between Z and T and YF and YO, then you have all YKs and you have the temperature. You can just read it. And once you have all that, you can run the rest of the code. There's a small trick here that I need to explain. In many of these codes, in a low Mach number code, usually when you do that in a low Mach number code, you can avoid using the energy equation because you have the temperature already from that. And you can avoid using the density because if you have the temperature and pressure is constant, you also have the density. So these two equations go away. The only one which is left is really momentum. So this code is very simple. It solves the three equations for velocities and the mixture fraction. Then you go into this little routine and you come back, and this thing can work. Now, you have to realize something is that this is a code for the DNS of these flames. Because if you want to do RANS or LES, there's a small detail here. These things here relate, for example, temperature to mixture fraction. They relate the instantaneous value of temperature to the instantaneous value of mixture fraction. But if you do RANS or LES, you don't solve for the instantaneous values, you solve for the averaged value. So then there's a small difference now. If you go to RANS or to LES, first now you're solving all these equations, but now you cannot say again that the mean temperature, if you know Z, the mean temperature corresponding to Z is not the temperature obtained for the mean Z. So you're going to need, again, now a PDF. So how do you do that? Well, you define a PDF of Z, and you use here the Z diagram and the PDF to obtain really the mean value of the fuel mass fraction and of the temperature. So the temperature, if there is a PDF of Z, as you can see here, you're not going to take this value, but you're going to take some average of these curves. When this is linear, it's not a problem, but when you are around here, of course, it may make a big difference. Now, this is nice, but how do you get the PDF? In the community, there's something interesting, is that the PDFs of mixture fractions, it's something that almost everyone agrees on how to model them. And everyone agrees that a good solution for the PDF is what we call beta functions. So beta functions have nothing, there's no link between beta functions and combustion. They are just expressions of a probability density function, which has the nice properties of being integrated to 1 if you integrate from 0 to 1. And it can be, according to the factors A and B that you see here, it can take all kinds of shapes. So for example, if you take a small a and a big B, this PDF is like a delta function at 0. If you do it the other way, you find a beta function, you find almost a peak here at z equal 1. And if you take a equal 0.1 and b equal 0.1, you have this. And a equal 2, b equal 5, you have that. So you can basically change the shape of the PDF when you change a and b. So the problem is, how would you find a and b? Well, there is a link between a and b and the average values. If you want this beta PDF function to recover the mean function of C and the variance of C, you have to pick up A and B like this one. A must be equal to this expression and B to this expression. Which means, okay, I can construct a PDF. I need A and B. I'm just telling you that instead of trying to find A and B, you can find these two quantities. This you know. You know the mean C. It's in your code. But you don't know the variance. So now you have to find the variance, which is common in these things. So how do you find the variance? This is for C. You can do the same for Z. So the way it works is the following. In your code, you must have the mean value of Z, or of C, it's the same, and the value of the variance. Once you have them, you plug them in A and B, and then you just have to compute the PDF. And when you have this PDF, then you can compute all the other variables. Okay? So that's all good, except that you still need to have the variance now. So let me show you how it's done. When you want the mean value of the fuel mass fraction, you're going to write here that this comes from the Z diagram, and P, you're going to say it's coming from the beta functions with these parameters I've shown you before. Now, how do you get the variance? This is where you have to pay a little bit. For those of you who know the epsilon equation, in the K epsilon equation, the variance is the same, but in the combustion world. So it's an equation which looks like this. There's a DDT of the variance, there's a convection term. Again, you recognize our old friend here, the turbulent diffusion modeled with a turbulent viscosity and a Schmidt number. And you introduce a new Schmidt number. And here there's a source term and a sink term. And those are models for scalar dissipation. And this equation has to be added to your code. I haven't said that, but if you talk about a K epsilon model, the K epsilon model usually will have rho, ui tilde, theta. And if you do a K epsilon model, you have an equation for K and an equation for epsilon. If you do a diffusion frame, it will be the same thing, but instead of that, you will use this. And what I'm just telling you, that if you want to use now this approach, you will need to have also the variance. So you'll have an additional equation that you need to solve at every time step. Those equations are written here. Again, constants to add here, constants to add here. And there's an additional problem with this equation is that it's very stiff and sometimes it's difficult to control. But that's the price to pay. So the code now will work like this. So this is what you have in your code. Dynamic pressure, it could be energy or temperature, what you want. The velocities, Z and its variance. And you need also K and epsilon. When you have all that, you can go, with this thing, you go into the PDF. You can construct the PDF. With the PDF and the Z diagram, you can compute the mean temperature, which gives you the mean density, and you can plug it here and keep turning. So you see that things are not too complicated, but they're getting a little bit complicated. Still, the interesting thing is that the code here remains reasonably simple because there is no source term anywhere. Absolutely no chemistry here. Look at this thing. All the chemistry is here. And it's a tabulation. So you don't have to worry about, you don't even, when you read the input lines of the code, there is no pre-exponential value, there is no activation energy. Everything has been done and hidden in this part here. So that makes life a little bit simpler. Now this simple model can be extended, and in the book you will find different versions of this thing depending on how you want to work. I just want to work on a few of them here and to comment on that one actually, the flamelet models. The flamelet models for diffusion flames follow exactly the same idea than the flamelet models for premix flames. You say, I want to introduce chemistry somehow, so I'm going to say that the mean reaction rate is the surface multiplied by the consumption here. The difference now is that for the premix flames, we had the premix flamelet. Now here we have the diffusion flamelet, which has been shown by Santanu, where you blow fuel on one side, oxidizer on the other side, and here you have the flame front. Now we know the consumption rate of this thing. We can compute how much it burns, and we're going to plug it into the model. So how do you do it in practice? It's a little bit more subtle. This is the equation for the fuel and species mass fractions. You recognize the diffusion term, which we're going to model with that guy. And now let's talk about this thing. So here, the new thing, compared to what we've done before, is that we recognize something which I said was very important, is that the flamelet like that one depends a lot on the stretch. Okay? If you blow hard on it, it will burn a lot. If you don't blow hard, it will not burn at all. So you need to introduce the effect of stretch. The way it's done in most codes is that we don't use stretch because it's difficult to compute. We use scalar dissipation. And so the reaction rate becomes a function of Z and of scalar dissipation. This you obtain from the flamelet which is here. You compute here. And you tabulate it. Once it's tabulated, you just need to know the PDF here, and then you can have the mean reaction rate. Of course, now the PDF is not one-dimensional, it's two-dimensional. So the way it's done usually, we use something which is not that clean, but that's state of the art. We say that the PDF of a two-variable like this is the product of the PDF. This is true if the processes are independent. You can prove that from statistical theory. It's not clear that Z and chi are independent, and because chi is the second derivative of Z. But whatever, again, we have no choice. P of Z, normally, like before, we said it's a beta PDF, and P of chi, normally we say it's log normal. It's just another form. And then the global code, which is doing that, gets a little bit more complicated again now. You get all these variables here. You have the mixture fraction and its variance, and you have k and epsilon. From that, you have a model for chi. That's a little bit tricky. And there, you construct the PDFs, the two PDFs. You get this from the flamelet, and then this gives you the reaction rates this time. In the previous solution, I was giving the temperature. Here, you give the reaction rates, and you plug the reaction rates here. So now you need reaction rates, but these reaction rates are computed outside the code using the flamelet and the PDF. So that's this information here. You have to compute first. You need another code, okay, a one-dimensional code for diffusion flames. You run it before you run your 3D code, and you tabulate this information. Now, I want to finish by a few words about real flames. Real flames are different. In real combustors, most models that you have derived for simplicity, because if you work in the academic world, you start by saying, okay, let us simplify that to begin with, and then we'll see later what comes out. This is why we look at the pure diffusion flame or the perfectly premixed flame. But when you go to a real system, then you have to account for other things, partially premixed flames, heat losses, radiation, and in that case, many of the strategies that we derived for simple flames just don't work. We have to find another way, and that's the problem. Because in real combustors, the first thing is that the regime is not known. There are very few premixed flames. There are very few pure diffusion flames for obvious reasons. Premixed flames are very difficult to do because you don't have time to mix. Pure diffusion flame is kind of stupid because they are not efficient, so you're always in between. You're always in partially premixed regimes. In most cases, the losses are important. You have losses to the walls because these flames are confined, so you need to model the losses to the walls. And that's a problem because the losses at the wall are basically changing your model. Remember, for example, when I started deriving this relation here, to do that, I used the temperature equation. Which was like this. And this equation means it's adiabatic because if there is here an additional term, a loss to the wall, for example, then or a radiation loss, then this equation cannot be combined to go there. So this equation holds only if you are adiabatic. If you're not adiabatic, you cannot do it. There's another problem if you want to work with mixture fractions, is that mixture fractions are defined only if all the Lewis numbers are equal, and we know it's not the case, but let's assume it is. But in many real systems, you cannot choose mixture fraction anyway because you don't have one or two inlets, but you have multiple inlets. If you have multiple inlets, one mixture fraction is not enough to combine all of them. So again, an example on this Siemens system. For a Siemens system like this, okay, those are monsters, okay? We're talking about meters diameter. You have 24 burners, that's one burner. That's one zoom on one burner. And this system is actually a system where you inject air through what they call the diagonal swirler, where you inject also air through the axial swirler, and you inject fuel in many places. That's a problem for mixture fraction. So you inject here, you have 4 air inlets, 2 here and 2 here, and you have, that's the 4 air inlets, and you have cooling at the lens. That's an additional problem. You inject air here. It's not much, but it's there, and it plays a role on the flame. You also cool the walls. That's another problem. Between the walls and the flame, there's some air coming in, and that's needed for the burner, but for the modeling, it's what you're going to do with this air. And you inject gas. Here in the diagonal swirlers, there are small holes which inject gas, but you also inject gas here in what they call the pilot gas nozzles. And in certain regimes, this is activated. And the guys who have imagined this system have the following idea. Here, you inject a little bit upstream of the chamber. So you hope that air and fuel is going to mix and lead here. This is swirl, so these gases will go like this, and they will burn here in a premixed flame. And 90% of the power is obtained this way. So it's almost premixed. Only almost. You cannot really say it's premixed. If you run it in premixed mode, you won't get the right result. The problem is these flames here, on both sides, is that they have a tendency to be slightly unstable. You know, they move a lot. So one way to stabilize them is to here have diffusion flames. That means you inject pure fuel, and in that case, you can stabilize the flame as if you would have a flame holder here, and you keep it stable. And so that really means that in a system like this, when it's operating, and what you see here is actually a computation with the second flame model, we see we have 2 types of regime in the same flow. Here we have almost pure diffusion flamelets, and here we have almost pure premixed flame, let's say at least partially premixed. And the model has to handle both at the same time. You cannot have a model here and another one here, okay? You must do the 2 things at the same time. So the model must handle at the same time a diffusion flame and a premix flame, and that's tough. The other thing also is that in many places here, like that one or this one, we have very strong heat losses. This is why this flame actually is not beginning here at the lips, because this lip is cold, and so the flame cannot come here. It has to be lifted a little bit. Again, if you have a model which supposes by the beginning of the demonstration that everything is adiabatic, you're stuck. You cannot move on that one. So one of the advantage of the sequence flame model is that this is done by the model. Okay. So just to give you an idea of how these things look, this is the geometry of one swirler. You can see how many blades are there. On each blade, you have 5 holes on one side. So in a geometry like this, we're talking about 100 jets in cross flow of methane mixing with air and then arriving in this chamber. If you look at the right-hand side, we computed first mixing in the system. That's the geometry of the full system. We started computing mixing only on a slice of that, so this part only. So you inject air from here, and here you have the holes injecting the methane. And you're going to see that it's mixing, but it's not fully mixed. This is the animation. You can see the 5 jets. Some of these jets actually merge together, which is bad for mixing. You can see these 2 jets together now. And there is some mixing. What we're looking at is an isosurface of fuel mass fraction. But you see that when you enter the chamber here, it's really not mixed. There is almost no fuel here. There's a lot of fuel there. So it's not a premix flame. So you have to handle that. So that's a view also of now the computation with all the blades at the same time. You can recognize all the jets here. So this is an isocontour of methane, and this is the flame front. And you can see that this isocontour of methane go into the flame front. If you would be perfectly premixed, normally they should be finished here, and you should have an homogeneous value here, but that does not happen. It takes too long to mix, so when it reaches the flame front, it's not perfectly premixed. So you need a model which can account for that. It's probably partially premixed. Same thing here for the case with pilot flames. You can see the pilot flames here. You see these pilot flames actually are very long. It takes a long time to mix, and the flame is stabilized here. So in that case, it's really, in this zone here, you have a diffusion flame, and you must be able to account for it. Okay, so that really means that depending what you do, okay, I know in this room there are people doing PhDs and people working for industry. If you do a PhD, you normally don't worry about that because you're going to simplify the problem to a point where you can use one model. If you work for industry, then you have to address the whole problem, and it's a different game because many of the simplified models are not going to work for your case. And then you have to face the fact that there's not that many ways to compute a real system. Okay, I'm just going to spend 10 minutes now beginning the next part of it, which is a little bit about the same topic, but now I want to talk about codes. I've shown you the equations that we need to solve. Now the question is it easy to solve these equations? And which code should we use to do that? So just a few questions here for the people in the room. Who is using or has already used the 3D code here? Not everyone, huh? And who has written parts of a 3D code? Less people, obviously, yeah, because it's... and who know what the dispersion and the dissipation of a scheme is? The numerical guys normally, huh? That's their job. Huh? The starting point of this business is the following. CFD has promised more than what it could deliver over the last 40 years or 50 years. And some people now just don't want to hear about CFD. For example, if you look at the safety of industrial sites, in France at the moment, CFD is just banned. You cannot use it. You cannot do a computation to certify that your installation is safe. For example, if you build a refinery just next to IATK and say, if there is an explosion, nothing will happen. If you do a CFD computation to do that, they are not going to believe you. They don't want to see it. Which means they do it just by, they guess. But why is it so? Well, because so many people have done so many bad computations that they feel it's no use. And it's a dangerous trend also in industry. You go to industry, you sell CFD, you come back 5 years later, the results are not good, they say, okay, it's not working, out. So it's really a problem today to recognize that we need to do good CFD, not only CFD. So Stanford has this famous sentence saying, not all LES are equal. Okay? The fact that you do an LES doesn't mean it's a good one. Okay? You need to do a good one, and that's much more difficult. Why is it difficult? Because even if it works, people in industry, they want to know, they always believe they can have everything from CFD. So for example, they don't want only the flame, they want the noise of the flame. They want to know how you ignite it, how you restart it. They ask all kinds of questions. We already have problems computing the mean flow, but they want to know all that, because the problem is that CFD has been going too slowly. We do what we can, okay, but that we're going too slowly, so these guys believe that it should be easy. So the first message about all this business is that we really need a precise CFD method. If you do a simulation and you don't really believe in it because you have tuned too many coefficients, it's not going to work, okay? So the method today clearly is going to be LES. The problem is that to do LES is not easy. It's already done in certain companies, not only in the lab. There are companies in France like Turbomeca doing helicopters. Actually, it's the world leader in the field of helicopter engine. In the combustion department, they have completely pushed out WANs. No one does any WANs anymore. They all do LES. But it took 10 years. 10 years during which we've been continuously comparing WANs and LES for every new engine until they found out that systematically they could trust LES and they could not trust WANs. Which means now that instead of paying a little bit of CPU, they have to find 2 million euros to pay for the CPU time. But that's 2 million euros, if you believe in your computation, is not a problem for them. Okay? The problem is, do you believe in the computations you have? And that's a major problem. The second problem is LES, is that doing LES today is still difficult and expensive. It's not, you go in the input file and you click on LES and you unclick on WANs and it's going to work. It's not true. And this is also not a task which can be done by people who don't know what they're talking about, especially in combustion. So this is what I'm going to discuss probably starting tomorrow. And I will first come back to what is needed for LES in terms of physical models. So basically, I will repeat what I said about LES, but that will be done in a different way. And I will talk about characteristic boundary conditions, because that begins to be a problem. Also about the fact that now we need to manipulate turbulence. In WANs, turbulence does not exist. Turbulence in WANs is K and epsilon. It's not turbulence. Turbulence, the real turbulence, is when things move. So when you do LES, instead of K and epsilon, now we need to generate turbulence. And you will see that this is an interesting topic. Then after I've done that, I will go to another question which is even more critical. What is needed for LES in terms of numerical methods? Can you just take a code and run it? Or what do you have to do so that your code will actually get the right results? It's not an innocent question. Actually, it's a strange coincidence that Takan Sengupta is working here. There's a whole bunch of people who have been looking at that for a long time. And, but in CFD of combustion, usually when you do a steady computation, it's as if nothing is moving. You just look at a steady flow field. As soon as you go to LES, you recognize that you're going to have eddies and waves. And the first question is, if you create an eddy in the flow, are you propagating it at the right speed? That looks like, of course, you say, of course, yes. Well, no. No. The point is that in most codes, if you're not careful, the speed at which you're propagating a vortex can be wrong by 50%. It's moving, but it's not moving at the right speed. So if you do an LES with a code which has errors like this dispersion and dissipation, then it's not going to be a good code. So you need basically to change that. Now, I will talk also about ghost waves, and that's also a big topic here. I know Takan loves this topic. I love it too. And I will talk about the effects of boundary conditions. I'll talk about the acoustic energy. And I'll talk also about the massively parallel codes. The point about that is that that's the drawback of this whole business. You say, I want to do LES. Okay, that's expensive. I want to do it with high precision codes. Okay, that's expensive. And at the end of the day, if I don't have a big computer, I just cannot do it. You know, just you run it and you say, oh no, it's going to take 2 years. So all these codes, all these methods have to be implemented in a massively parallel world from day one. AVBP, the code I'm going to show tomorrow, was written parallel from the start, you know, because you cannot take an existing code and make it parallel. It's just too complicated. So you have to think that when you go this way, going to computer science experts is a good idea from the beginning, because that part can kill you. This part is really awful. You know. This part is really what makes your life miserable. If you're a PhD and you have to worry about this thing, you have to learn about message passing and all this business. It's complicated. So this is what I will do, and I'll probably do that tomorrow. I think for today you probably have enough. So if you have any question, we can do them now. Otherwise, we'll meet tomorrow morning. Questions? Yeah. It's the same. Huh? It's the scale dissipation is only one. It's the 2D grad z square. It's this one. Yeah, there was, okay, it's the same too. Scalar dissipation is the source term of the, is the dissipation term in the variance equation. You're right. It's, so if you look at this equation here, this one, this is also scalar dissipation. It's a model for scalar dissipation, because the scalar dissipation, again, is a subgrid scale quantity, and you have to model it. So you model it as a function of z prime square. It's another trick of the, you know, if you look at this equation, what it really means is that you assume that, that's a little bit technical, huh, but you assume that chi over z prime square changes like epsilon over k. Because this is the dissipation of the vortices, this is the dissipation of the scalars. So you say, okay, they scale in the same way. So this is why you obtain chi equals z prime square epsilon over k here. And again, this is a model. And you have to tune the constant. Yeah. Of course. That's the job.
So I have a question.
Sure.
How do you generate the flamelet for the premix trains?
For the premix case, you normally, if you use the simplest model, you don't use the flamelet equations. You just need the flame speed. You say, so you need to pre-compute the values of the flame speed. That's all you need.
So, for example, if there is any strain there in the flame.
Okay. You can go one more step, but you see, that's another thing which has been done also quite often. If there is a flame like this, that's the flame front. Certain parts of this flame front are stretched, but certain parts are compressed. And the very interesting thing actually is that when you do the PDF of stretch on a flame like this using DNS, you find something like this. So you find that there are places here which are compressed. So this point, for example, maybe will have a less surface a few milliseconds later, and this point will have more. But on average, there will be a little bit more stretched than compressed, because otherwise the surface would not grow. So it looks like all the flames are turning themselves so that they always prefer to be stretched rather than compressed. Which really means that if you want to incorporate now the effect of stretch on the local consumption speed, it's kind of difficult, because those flames depends on the Lewis number, but typically those flames will burn more and those will burn less, or the other way, and you average that. And so again, you need to find a model for SL of the mean stretch. You might know the SL of the local stretch, but what you want is the mean, and that's difficult. So in many cases, what we end up doing is to say there is no effect. This is SL0, because in the DNS, what we see most often is that the average SC is maybe 20% off, you know, from the consumption speed, so we don't change it. But there might be cases where it's not true. If you do hydrogen, For hydrogen, it seems that you can shift a lot. Again, to first order, we don't take that into account.
See, actually, I'm interested to do some simulation for the stratified combustion.
Yeah,
You know that the equivalence ratio is changing,
yeah.
and then could you suggest that how to approach this for using some blended kind of model?
Yeah. I think that if you do a premix flame, it's sufficient to take into account stratification, not stretch. I would start with stratification alone. So with this curve, you know, SC as a function of local equivalence ratio, like this. One. Yeah. If you use that as an input in your code, there's a small trick. You have to find. You have to be able to find the equivalence ratio. You have to use the mixture fraction. You go through the mixture fraction and you can find the local equivalence ratio at each point, including the burnt gases. And then you go here and you read the SC.
So, is there any model which can handle the both premix as well as premix as well as non-premix, apart from PDF?
Yeah, well, there are models. There are really sophisticated models in the world of piston engines. In piston engine, there's a model called CFM 3Z for 3 zones, which includes both diffusion, premixed, and auto-ignition models for WANs. So if you go on the web and you look for that, it comes from IFP in Paris. And the problem is that it's a very complicated machinery, okay? It's very heavy to manipulate. We don't use it. I don't know. Of course, the PDF models can do that, if you find the PDF.
Can't we use the assumed PDF, I mean presumed PDF?
Yeah. That's when I use the beta PDF model. That's a presumed model. I say the PDF looks like this, but the DNS show that the beta PDF is reasonable usually. I think the weakness is not in the PDF. The weakness is in finding the variance, because you've seen the equation for the variance is a model again. Once you have the good variance, I think finding the PDF is probably reasonable. Finding, you know, once you have this thing here, then that's okay. I mean, the main problem is how do you find this thing? How do you find this guy here? That's tough. Question?
Even the ECFM 3G that is believed to simulate both premix and we worked on it for 2 years and observed that in cases where we had both premix and diffusion, it was not actually capturing the premix part very well. So they came up with a newer model.
Yeah.
I mean, I still don't understand how that works. They call it CLES or
Yeah, I know. They're trying to do something complicated. Okay, it's.
One question I had was, do they consider the kinetics in it, or do they have the mixture fraction versus equally speed, tabulated speed?
Well, it depends what you want to do. You're talking about piston engines here. Tabulation in piston engine is really difficult because everything is changing. You have dilution, pressure, equivalence ratio. So the table gets huge, and they're coming back from tabulation at the moment. It's just very complicated. But it's true that the piston engines, I mean, it's bad luck. I mean, you guys pulled the wrong case. It's really the most difficult case. You have everything at the same time. Much easier to do a gas turbine. So in the piston engines, people are still fighting to imagine what could be the model. And at the moment, CFM3Z is really the basic standard that you find in most codes. You know, even Converge will have it soon. So that's probably a reasonable choice.
So, in case of, I mean, consider effects like blow off and quenching, how accurately you can predict with the Ransomware? Or can we predict with RANS?
Well, quenching. Well, if you're using the eddy breakup model, it will never quench. Okay, so which means that now, if you want to have quenching, you have to introduce it somehow. And the way you do that, it depends on what you believe is important, you know. So you can have things like if the occurrence ratio is too low, you bring the constant to 0. But after that, it's all going to be a model, okay? Some people tried, for example, in flamelet model, some people do what Santanu just asked for, which is they give a model for SL as a function of stretch. So they say if the mean stretch is too large, then there will be quenching. You can do that. But honestly, I think it's very difficult to capture quenching in a one's code because you have to, first you have to identify what's the mechanism leading to quenching. I don't know which configuration you're talking about, but in most cases, one just doesn't see those things. I don't believe it can be done easily.
EDC model, does it take care of the finite chemistry?
Well, EDC is one name, but there are many implementations of EDC. So you have to look at the implementations you have. Normally in EDC, you have some kinetics somewhere. It's a combined expression with kinetics and some eddy breakup formulation. So there is some kinetics there, yeah.
So if there is kinetics, can it not take care of the
It can, but you know, it's not based on any, when you take the minimum of two models, for example, why not? Why not take 1/2 of the two or 2/3? Or it's not based on scientific arguments. So you may tune it so that it does what you want in a few cases. That's what people have been doing. There are a few papers now with EDC to do LES. And yeah, why not? Today the status is that if you want to believe in the model, you have to test it in many cases. Showing it works in one case is not interesting. And of course you have to promise you won't change the constants. It's all in the constants. It's
How do you take care of the constant? Because in my case, if I take care of the default constant, the flow field after some iteration flow field changes drastically. So the problem the figure was changing the constant and changing theta more. I think the flow field was stabilized. It was able to give.
yeah, but you see, it's that's the main problem of the community here is that since you can change things, you change them to make the things work. But probably you are just compensating here a default of the model by changing a constant. But then that diminishes your capacities of feeling that you could pass a blind test, for example. Because you say it's better because you know what you should find. If you would not know what you should find, what would you do? You would not have an idea, you know, if your model is right or not. This is why today it's time to go back to an idea that you should not change the constants, or you should not change them more than once. You know, you fix the constant for the model, and then you try not to change it. And if you want to change something, you have to change the model. That means the model is not universal. You need to build another one. If you start changing the constants, some people do that. Some people have libraries of constants. So they have one constant at 1 bar, one constant at 10 bar, one constant for lean, one constant for rich. Yeah, it's been published actually. I have a paper for eddy breakup where the guy published a table of constant in a matrix. You can pick up your constant. It's you know, it may not be that stupid if you're not interested in the scientific aspect of the problem. Just want a tool to be able to reproduce certain things. Why not? But from an academic point of view, it's no interesting. I don't want to do that. Changing the constant, especially if you change the constant by a large amount, should tell you that something is strange. I mean, it should not be done. But for eddy breakup, the constants are changed by a factor of 1,000. Eddy breakup, typically you have to go from 1 to 1,000 to make it work.
In EDC concept, I know the temperature shoots up beyond 5,000. Why is that?
Oh, okay. The problems of the temperatures going too high is not a problem. Usually it's a numerical problem that the reaction rate has become too large at one point, going to crazy values, and then temperature overshoots 5,000. Normally it's a lack of resolution. That we are exactly in what I was describing before. If the flame front gets too thin, then the code just explodes. It's like computing a laminar flame with not enough points. You need points. You know.
Do I need to make field size more refined?
You probably need to add some points. That's unfortunately, that's very often the problem.
One of the groups there's some marker stuff which works on certain reactive models. So this they publish results using stochastic reactive modeling and they show that they are very good. Is that does it consider certain turbulent parts or is it more kinetics based? How will you explain
Depends what you're talking about. You're talking about well-stirred reactors, or
well-stirred?
yeah. When you do well-stirred reactor, you don't do CFD. Actually, you just do a stochastic tracking of one particle in the reactor, and you do many of them, and you average all of them, and that gives you the result for the average quantity. But that's really, it's a methodology which works only for the well-stirred reactor. You cannot do anything else with it because it works only if the flow is homogeneous, and you can only track particles in a Lagrangian way. But in a gas turbine, for example, you cannot do that.
Another question I have is the PDF methods that generally what I understand from the statistics is method moments is slightly better, sectional methods is better. Then we have Monte Carlo simulation. Will anyone try doing such a stuff for this turbulent formation or is it too complex to handle?
Yeah, you can use Monte Carlo methods. If you do PDF methods, you will use Monte Carlo methods. But again, this gets really fast out of control in terms of CPU time and complexity. So you will find people doing that, but I don't believe you're going to see that in industry pretty soon. It's expensive. Sure.
When vortex lights up, it increases the pressure wave. So if I just want to see in a very simplified case, how is the pressure evolving because of breaking up of vortex? What parameter should I look for?
If you just want to look at what? At vortex breakup?
Yeah. So what is the rise in the pressure wave, the acoustic effect of breakup of vortex? What parameter should I look for?
What's the physical problem you're looking at? It's,
Small reacting flow,
yeah,
vortex shading from the rough body depth.
yeah.
So if I just take one of the vortices of a number of vortices, I just want to see the delta P rise in that. Because I don't know the phase, how it affects, what parameter should I look for? Because acoustics get affected because of the breakup of.
So you're interested in the noise emitted by the vortices behind the flame holder. Well, again, you need a compressible code and you need an LES code because that's.
Should I look for only to relate the timing of vortex shed and the delta P rise?
Well, the only thing you need to specify if you do that is the subgrid scale model for the flow. Now, there are a few models, the Smagorinsky model is the most classical, and normally that should be sufficient. Smagorinsky probably does the job. I would not do more. But then it's really the code itself, which has to be compressible and high order, because if you want to measure noise, it's tough. Yeah, I will talk about that tomorrow. High order means probably more than 2. 3, 4, 5, 6, whatever, but 2 is, I will show tomorrow that there's a big difference between 2 and more than 2. 2 is a bit low for vortices.
The technique for generation, stable generation, how many number of generations actually could be optimal for any flame? How many number of generations?
How many number of what?
Flame rates.
Oh, well, it depends. Depends how much you want to pay for it. Usually, in these tabulation methods, you tabulate only 10 to 20 flamelets because it's not a stiff function. It depends again if you want to go to quenching. If it's a diffusion flame, you have to go to this part of the region where you have scalar dissipation and total reaction rate. It goes like this, and then it quenches here. So you might have to tabulate more flames here to be sure that you capture quenching.
And that we have to work at maximum scalar distribution step related to quench.
Those are steady flamelets, huh? Those are steady flamelets, so you can run them with a 1D flame code normally. But that doesn't take time, okay? It's not complicated. Other questions?
So do you also talk about the hybrid GANs and LES approach?
Hybrid?
Hybrid GANs and LES.
Oh, you mean DES, methods like this? Not really. We looked at these methods, but they're really for aerodynamic problems. In combustion, the DES, for example, is difficult because the geometry of our chambers is very complicated. If you look at a swirler, it would be very difficult to isolate the part which should be RANS from the parts which should be LES. You know. So in practice, we'd rather do LES everywhere.
No, near wall treatment, for example.
Yeah, and at the wall we use low of the walls. Low of the wall is like, it's a little bit like a hybrid method, except you do LES everywhere, and at the wall you use the low of the wall. And around an aircraft, I think DES is much more adapted, but in a combustion chamber, we don't use it. I know that some codes can do that, yeah, using DES.
And also linear AD modeling.
Okay, linear AD model I did not describe. Linear AD model is really a different view. Huh? You need to solve 1D problem per cell in your computation, and that's supposed to account for mixing and turbulent combustion at the subgrid level. I think again it's a complicated model for many chambers. It's very expensive, and Georgia Tech is doing it now, and Sandia keeps doing it, and but that's about it, and not that many people try that. I think it's a complicated model to run. We haven't tested it. Some
In the both regime, right?
yeah, the linear AD model should account for any type of flame at the subgrid level. Yeah, because it does
Just
not.
like you described, Higgin flame model that would be applicable in both the regimes, the linear AD modeling.
Yeah, LEM can do normally any regime. That's true. Yeah, including chemistry. So that's a good aspect of it. Yeah. Yeah, I did not describe all models. I mean, that would take forever. Huh? So, no question? So we meet tomorrow morning. Have a good evening.